In today's lecture, we are going to see the last method of this course, which is called as the Runge-Kutta method, that is used to solve a differential equation. And like before, we are going to deal with the differential equation of a first order, which has the form dy by dx equal to some function of x and y. So we want to solve this differential equation and evaluate the value of y for some value of x given some initial conditions. So we want to evaluate y of x for some value of x. Okay, and let's do an example. The procedure in Runge-Kutta method is an iterative procedure, but what it does is it kind of during the iteration reduces the step size to half. The smaller the step size, the more accurate our solution is going to be. So Runge-Kutta method indirectly reduces the step size within the same iteration and thereby improves the accuracy of the solution, because the smaller the step size that we take when moving from the initial point to the final desired answer, the more accurate our solution is going to be. But a smaller step size means that we have to perform more number of iterations, right? So Runge-Kutta method reduces the step size by half as compared to the previous methods we have seen. So we have a differential equation which is a function of x and y, and then we have some initial condition, okay, given initial condition y of x naught equal to y naught. So we are given x naught and y naught, and we are asked to find y of some x, okay, let's say x5, using step size h. So this will be provided to us in the question, and we need to move from x naught to x5 in steps of h. So suppose x naught is 0 and x5 is 0.5 and h is 0.1. Then from 0 to 0.5 we have to take steps of 0.1. So we'll have to do 5 iterations. From 0 we'll go to 0.1, 0.2, 0.3, 0.4, 0.5. So that means it's going to take 5 iterations to go from 0 to 0.5, for example. But if we reduce the step size from 0.1 to say 0.05, then it's going to take us 10 iterations, because we have to go from 0. The first step will take us to 0.05, then 0.1, then 0.15, then 0.2, and so on. So that would take us 10 iterations to get to 0.5, right? So smaller the step size, it's going to take us more iterations to get to the solution, but at the same time, the smaller the step size, the more accurate our solution is going to be. So depending on the application, whether the application requires higher accuracy or a faster solution, we need to choose the method appropriately. Okay, so let's do an example for the Runge-Kutta method, and we'll try to get the answer and compare it with the other solutions that we have computed previously. So the procedure is, given the initial values x naught and y naught, we will find the new value, which we'll call as x1 equals x naught plus h, and we'll compute the new value of y, which we'll call as y1, as y naught, plus a parameter called as k2. So we define this parameter k2 as where k2 is given as h into f of x naught plus h by 2, comma y naught plus k1 by 2. So you see now we are evaluating the slope, which is f of xy. dy by dx is the slope, which is given by this function of xy. So we are evaluating the slope at a point half the step size away from the initial point. So x naught plus h by 2, and correspondingly there is y naught plus k1 by 2. Now we have to define what is this k1. So where again k1, where k1 is h into f of x naught comma y naught. Okay, so h into f of x naught y naught is the same parameter that we add to y1 in Euler's method, right? So we first compute the additive term that we add in Euler's method. Then using that, we compute another new value which is called as k2, the value that has to be added, and then we add that value to the initial value of y, and that gives us the new value of y for that particular iteration, and we keep repeating this iteratively until we get to the desired value of x. So that's the procedure for Runge-Kutta method. So let's do an example, and I'm going to use the same example that we did previously for Euler's method and the modified Euler's method. So our example was dy by dx equals minus x y square, given the initial condition we had is given y of 2 equals 1. That means x naught is 2 and y naught is 1. Okay, we are asked to find y of 2.3 using the step size h equals 0.1. So that's our objective, to find y of 2.3 given that when x equal to 2, y is equal to 1. We are asked to find when x equal to 2.3, what is the new value of y, that is y of 2.3. So for the procedure, we need to first compute k1, then k2. So to compute x1, it's just adding h, but to compute y1, we need k2, but to compute k2, we need k1. So we will first compute k1, then we will compute k2, and then add it to y0, so that will give us the new value y. So the first step is to compute k1. K1 is h into f of x0, y0. H is given to us as 0.1 into f of x0, y0 is minus x0, y0 squared, because the function we have is minus xy squared. So in place of x, we put x0, and in place of y, we put y0. Okay, so that is equal to 0.1 into minus x naught or x0 is 2 into y naught is 1, so it's y naught square, 1 square. So that gives us k1 to be equal to minus 0.2. Next we are going to compute k2. To compute k2, we need to first find the slope of the function at x naught plus h by 2 and y naught plus k1 by 2, and then multiply it with h. So we will compute that slope first of all. So f of x naught plus h by 2 comma y naught plus k1 by 2. So that will be equal to f of x naught is 2 plus h is 0.1 by 2 comma y naught is 1 plus k1 is minus 0.2 by 2. So we are going to evaluate f of x naught plus h by 2, y naught plus k1 by 2. So that is going to give us f of, that's 2 plus 0.1 by 2, 2.05 comma 1 minus 0.2 by 2 is 1 minus 0.1, which is 0.9. So we need to evaluate f of 2.05 comma 0.9. So from that we will write k2 as h into f of 2.05 comma 0.9, which is equal to 0.1 into minus xy square. So in place of x we will put 2.05 and in place of y we will put 0.9. So it will be minus 2.05 into 0.9 square. So that will give us minus 0.16605. So that's our K2. So once we have this value of K2, we can now compute our value Y1. So Y1 will be equal to Y0 plus K2, which is 1 plus minus 0.16605, which is equal to 0.83395. Okay, so that is Y1. The corresponding X1 is X0 plus H, which is 2 plus 0.1, which is 2.1. So when x equal to 2.1, y equals 0.83395. So that means y of 2.1 is equal to 0.83395. Okay, so that's our first iteration completed. So y of 2.1, we get it as 0.83395. Now I want you to compare this with the y of 2.1 we got previously in the previous lecture using Euler's method and modified Euler's method, and also compare it with the exact analytical solution that was shown in the previous lecture as well. Okay, I'm not going to do that here, but I'll leave that as an exercise for you to compare and see whether this method is actually giving a more accurate solution or not. Okay, and you will see that indeed this gives better accuracy as compared to the previous methods. So next we will now compute the second iteration. So in the second iteration we will have x2 equals x1 plus h, which will be 2.1 plus 0.1, which is 2.2, and correspondingly we will also compute the new value of y as well. Now the new value of y, which we'll call as y2, is going to be equal to y1 plus k2 again. So we call this added term to the previous value of y as k2, and to find k2 we need k1 first, right? So k1 is equal to h into f of x1 y1. Okay, previously when we computed k1, it was h into f of x0 y0. Now k1 is h into f of x1 y1, because we have the new value of x and y, which is x1 and y1. So we'll use that to compute the new value of k1. So that will be equal to 0.1 into minus x1 y1 square, because our function is minus xy squared, and that will be equal to let me write it in the next line. That will be 0.1 into minus x1 is 2.1 into y1 is the previous answer we got, which is 0.83395. So that's 0.83395 square. So when we compute that, we get the value of k1, which is equal to minus 0.14605. So that's our k1. Next we want to compute k2, which is h into f of x0 plus h by 2, comma, in this case it's not x0, it will be x1. So it will be x1 plus h by 2, comma, y1 plus k1 by 2. So that will be equal to h is 0, 0.1 into f of x1 is 2.1 plus 0.1 by 2, comma, y1 is 0.83395 plus k1 by 2. Okay, I'm just going to write that in a separate line just to keep things clear. So that will be equal to 0.1 into f of 2.1 plus 0.1 by 2, comma, y1 is 0.83395 plus k1 is minus 0.14605 by 2. So that will be equal to 0.1 into f of 2.15, comma, and you evaluate the right hand side there, you get it as 0.76093, 0.76093. So that will make it as 0.1 into minus xy squared, minus 2.15 into 0.76093 squared. So that gives us K2 to be equal to minus 0.12449. Okay, so that's K2, and now we will get Y2 is equal to Y1 plus K2, which is equal to Y1 is 0.83395 plus K2 is minus 0.12449, which is equal to minus 0.70946. No, not minus, it's plus, okay. That's 0.70946, okay. So when x equal to 2.2, y is equal to 0.70946. So we can write that as y of 2.2 is equal to 0.70946. Okay. Now we are asked to find y of 2.3, so that means we have to do one more iteration. If you are asked to find y of 2.4, then we will have to do two more iterations, and so on. Okay, depending on what has been asked, you have to do that many iterations. So we have now obtained y of 2.2. So we should now compute y of 2.3, and that will give us the solution that we desire. So for the next iteration, we will have x3 equals x2 plus h, which will be 2.2 plus 0.1, which is 2.3. And then for this iteration, we will compute k1, which will be h into f of x2 y2. Okay, so because we now have x2 and y2 available to us, we know x2, we know y2. Previously we computed f of x1 y1. Now we will use f of x2 y2 into h. That will give us the new k1 for the third iteration. So that will give us 0.1 into minus x2 y2 square, which is equal to 0.1 into x2 is 2.2 into y2 is 0.7046 square. That's 946. Okay, so that gives us the new value of k1, which is minus 0.11073. Okay, so that's k1. And then we have k2, which is equal to h into f of x2 plus h by 2 comma y2 plus k1 by 2. So notice here we have used x2 plus h by 2 and y2 plus k1 by 2 because we have x2 and y2 available from the previous iteration. So we'll use them to compute the new k2. So that makes it 0.1. H is 0.1 into f of x2 is 2.2 plus 0.1 by 2 comma y2 is 0.70946 plus k1 we have obtained here, which is minus 0.11073 by 2, which is equal to 0.1 into f of 2.25 comma 0.6541. So when we compute this, we get 0.6541. So that will give us 0.1 into minus 2.25 into 0.6541 squared, because our function is minus xy squared. So that gives us the value of k2 as minus 0.09627. So with that we can now compute y3 as y2 plus this k2, which is equal to 0.70946 minus 0.09627, which is equal to 0.61319, 0.61319. Okay, so we have y of 2.3 as 0.61319. So when x equal to 2.3, y is equal to 0.61319, and that is exactly what we have been asked to compute in the question. So the question says, given y of 2, find y of 2.3 using the step size. Okay, and what we notice is in each iteration we are computing an intermediate slope which is half the step size away from the initial point, right? So h by 2 indicates that we have moved from the initial value of x, we have gone half the step size. So indirectly we are reducing the step size and trying to improve the accuracy of the solution. So that's our y of 2.3, which is the desired answer, which is equal to 0.61319. Okay, so if you're asked to do calculate y of 2.4, then you'll have to do one more iteration in the same way, and that will give you y of 2.4. And again, check the solution that we obtained for y of 2.3 using Euler's method, which we did in the previous class. Euler's, modified Euler's, and from today's lecture for the Runge-Kutta method, and compare these answers with the exact analytical solution that I have given in the previous lecture, and see which of these methods gives the highest accuracy. That means which of these methods gives an answer which is closest or nearest to the exact analytical solution. So if you I'm not going to write it here, but the exact answer is 0.6079, and by this Runge-Kutta method we are getting it as 0.61319, and using Euler's we got it as 0.5681, and with the modified Euler's we got it as 0.6297. So clearly this Runge-Kutta method is giving us a better accuracy as compared to the previous two methods that we have seen. Okay, so that brings us to the end of the topics in this course, and You have your midterm exam in the next week, so prepare well for that. And I've also announced a quiz on Blackboard, so make sure you do the quiz which is announced for this weekend. Check the announcement, and you'll have 2 more quizzes, so there'll be a total of 5 quizzes, and I'll take the best 4 out of the 5 quizzes. Okay, so you'll have 1 quiz this weekend and 2 more quizzes in the next weekend before your final exam start. And make sure you prepare well for the mid exam as well as the final exams. Okay, if you have any questions, we can have a discussion now regarding any questions that you might have.